Okay, this is our Intro to Matrices lesson. And I kind of want to set up the lesson just by talking about some stuff we already have been working on. We've been talking about systems of equations. We did 2 equations with 2 variables, 3 equations with 3. And I'm just going to make up a random one. I don't know if it works, if it doesn't work. I don't know. We're just going to go with it. So we have been solving systems like this by hand, right? We did elimination 2 times. We picked 2 combinations of 2 equations. We did elimination to go from 3 variables to 2. And then that gave us 2 equations with 2 variables. We did another round of elimination to go from 2 variables to 1. And then once we got down to 1 variable, we solved for it. And then we back substituted, I don't know how to pronounce that. And we solved for the remaining 2 variables. Now, that was a lot of work. And matrices help us simplify or streamline that process. And the main way they do that is by removing the variables. So I'm going to write a matrix of this system. Now, we haven't reviewed matrices together yet, so I just want you to look at what I'm about to write and see what similarities you can find, okay? And then the main point of the lesson is to review the vocabulary and the way of identifying certain parts of matrices, and we'll talk about that. First, let me just show you and see how you feel about it. So just pause your video if you want a minute to think about this and just compare what I wrote in black to what I wrote in blue and see if you can figure out what kinds of things are going on there. Here's some stuff I hope you noticed, okay? For one, the matrix is all around you, just joking. The matrix has brackets, bless you. The matrix has brackets here. It has, just like our black system that I wrote in black had 3 equations, this system has 3, what we call rows, going across horizontally. The matrix has this straight line right here. Sometimes it's a dashed line. Notice that that corresponds to where the equal signs are. And then all these numbers on the left of that are the coefficients of the variables on the left side of the equations in our system. And all the things on the right of that line are the constants from this side. And we can do the same kinds of math on the system and we can do it on the matrix. So like, for example, let's say you were looking at the system as I originally wrote it, okay? How we've been working over the last few weeks. And let's say you wanted to eliminate the X's in row 1, in the first row and the second row, okay? It would be really great, right, if this X right here had a -2 on it. And I can make that happen by multiplying everything here by -2 and then adding these 2 rows. I can do that exact same math on this matrix. I can multiply everything here by the -2 and it would change it. 2, -12, +1, and -10. And then I would just add these rows together and I would eliminate the X in one of those rows, okay? Now that might have gone over your head, that's okay. This is just an introduction. I'm gonna go over this all way more slowly, but I just wanted to give you an idea of where we're working towards as we start this lesson, okay? So we're moving from systems into matrices, and in the past, depending on what math you had. Not sure you've done matrices by hand before. You've used the graphing calculators. Well, we are going to be doing them by hand, and it's a whole nother thing. And you're going to be just fine. So we're going to start by just talking about basic notation and vocabulary about matrices. Okay, so this example here is just a regular matrix. Notice in this example, there's no bar with other numbers on the right-hand side, and I'll explain more about that later. Instead, we just have this regular matrix, and we're going to talk about some vocabulary, okay? The first thing we're going, oh wait, hold on one second. Where is mine? I'm going to pause the video. I think I'm sorry. I hate to sit here and record myself. Okay, here we go. Just the basic definition of matrix is that it's a rectangular arrangement of numbers in rows and columns enclosed by brackets. So we talked already about rows and columns, and you saw that the matrix, I put brackets around it, right? They're really big, tall brackets right there. We name a matrix with a capital letter, like it'll be matrix A, and it'll be capitalized, or matrix B, something like that. The number of rows and columns that a matrix has is called the size. It's sometimes called the order. It's also sometimes called the dimensions. So you'll want to get comfortable with all three of those words. They all mean the number of rows and the number of columns. And we always talk about the number of rows first and the number of columns second. So that original example I gave you, it had 3 rows and 3 columns, unless, I know I'm about to confuse you, but unless you're talking about the constants on the right-hand side, and then that would have been 4 columns, and I've already said too much, so I don't mean to confuse you. One thing I do want to point out right now is when you're talking or reading in your head about the dimensions or order or size, this X right here doesn't mean multiplication, it's the word by. So we would say they're number of rows by number of columns. We would say it's a 2 by 3 or a 4 by 4 or something like that. And here's where I want you to remember that rows are horizontal and columns are vertical. And I think columns is the easier one to remember first, because if you think about columns on a building, they're vertical, right? And so if you can always remember that columns are vertical, then by default, rows are horizontal, left to right. Columns are up and down. And then another just random thing that always pops in my head is I think about making just like a cross shape, like columns go up and down. And rows go across. That helps me. I think it's a little bit arbitrary. It might not help you, but whatever sticks, I'm just throwing stuff at you. So those are some basic vocabulary and ideas about matrices. And you'll want to get these ideas down as fast as possible, because as we start working through problems, we're going to be using, your teachers are going to be using these words: size, order, dimensions, rows, columns, you know, making sure things have brackets. You'll want to get these ideas down quickly. Okay. All right, so now this screen is just about some more notation. We have an example matrix right here. The first sentence matrix A is blank by blank. We want to know how many rows by how many columns. So take a minute, pause the video if you want to get that in your head before I tell you. Go ahead and pause now and fill that out. So matrix A, remember it's rows first, columns second. The rows go horizontally left to right. So we have one row here and a second row here. So there's 2 rows. And columns go vertically up and down. So I've got 1, 2, 3 of those. Let me erase that so we can see those better. Okay. So then this next sentence says the numbers in the matrix are called entries. And how many entries do you see in this matrix? 6, right? There are 6 matrices, 6 up. Goodness gracious. Miss Fadia's talks, take 2. There are 6 entries in this matrix. And the entries are represented by A, so that's a lowercase a. So the name of the matrix is capital A. We said that matrices are named with capital letters. Okay, but so that's the matrix as a whole. Each individual entry is named with a lowercase a, and then it has this subscript, I, J, where I is the row that an entry is on, and J is the column that it's on. So this just one simple example. If I wanted to know what A sub 23 is now, this is not A sub 23. This is row 2, column 3. It looks like the number 23, but it's just 2 individual numbers that mean 2 different things, okay? Row 2, column 3. So we go back up to our matrix and we find what's in row 2 and column 3 at the same time. So here's row 2, here's column 3, and where they intersect is the -5. So that's the entry at that spot. So pause your video right now and just take a moment and figure out the dimension, size, order of these 2 matrices, and then also identify, so you're determining the size and the entry in the first row and second column. So take a moment and do that. So for the B matrix, the first thing you're finding is the size. It's rows by columns. They happen to be the same, 2 by 2. And then for the entry, so to name an entry, use the lowercase letter, so lowercase b, the first row, second column. So first row, second column, that's 3. And then for the other matrix, the first thing is the dimensions. It's got 3 rows by 2 columns. And then the entry that's in the first row, second column. So you use a lowercase c, first row, second column is -7. And now we've talked in the past how you can only solve systems where it's got the same number of equations as variables. So if you're solving for 2 variables, you need 2 equations. 3 variables, you need 3 equations. And this idea leads us into, or this requirement leads us into the idea of a square matrix, right? Where the equations match the number of variables, they're equal. And so when we talk about this new vocabulary, a square matrix, we would say that a square matrix has the same number of rows and columns, right? So that's equations left to right, matching your variables that are going up and down, your rows of your columns of X, Y, and Z. And then when we start solving matrices in the next few lessons, we're going to be talking a lot about the diagonal of a square matrix. And we won't have too much context for that today. Today, we're just introducing you to the idea. But the diagonal entries are the values on the diagonal from the top left corner to the bottom right corner of only square matrices. And this will be a concept that we talk more about today and as we start solving. Okay, so just to practice the idea of a diagonal, identify the diagonal entries of the square matrix below. You can pause your video if you need some time to do that. Hopefully you came up with this diagonal. The answer would just be 2 or -2. All right, so now here's in symbols and variables what I was talking about with you at the very beginning when I gave you that introductory real fast example. So we have this linear system here. There's no actual numbers. The numbers will go where A, B, C, J, R, for example. If you make a matrix from just this side, that means you're dropping off all the X, Y's, and Z's, and you're leaving just the numbers in front of them. We call those the coefficients, right? If you did that, and you put brackets around it, because all the matrices have brackets, you would get this right here. And then if you made a matrix with just the constants on the right-hand side of the equations and put brackets around it, you would have this matrix here, right? And so we're going to call, and this is simple, right? We're going to call the one made with just the constants, we're going to call that the constant matrix. And the one made from the coefficients in front of the variables, we're just going to call that the coefficient matrix. Pretty simple concepts right there. Side note, if any of your linear equations do not include all 3 variables, so let's say you had one of your equations that you're trying to make a system for was just 2x plus z equals 4, right? But you're trying to fill in all the entries in your matrix, you would put a 0 in the coefficient matrix in its place. So when you were to do a row representing that equation, you would say that the entry for the x is 2, the entry for the y is 0, for z is 1, and then your constant matrix would have a 4. And the coefficients are always in the order x, y, and then z. So an augmented matrix is when we combine the coefficient and the constant matrix into one. And it says dotted line. A lot of times we use solid line, so just make sure it has a line right there. Remember, I talked about in that introductory example, that's sort of like representing the equal signs in your system, okay? And then this column here is your x's coefficients. The second column is your y coefficients. The third is your z coefficients. So this right here is your coefficient matrix. And this right here is the constant matrix, and they're just been combined into one with a line that separates them, and we call this an augmented matrix. And now we're going to do some work with augmented matrices, help us solve systems. And we're going to start looking into that. All right, so this first example says, form the augmented matrix for the following system. Also, name the diagonal entries of the coefficient matrix. So pause the video and you try that on your own, and don't unpause until you've tried it, okay? Because if you watch me do it, you'll think you understand 100%, but maybe you don't. So try it on your own first before checking with me. So here's my augmented matrix. The only mistake I can foresee you probably making is on the third row, because see, it's missing a variable, but the 4x is lined up with the y's. So you might have written for your third row 0, 4, -2, but that just means you're going too fast. Slow down and look. It's actually the x that we have the 4 on. So the 4 should go in the x column. We have no y's, so 0 goes in the y column, and then -2 in the z column. And then remember, diagonals are only on square matrices only. So we're not finding a diagonal of the augmented matrix. We're finding the diagonal of the coefficient matrix because it's a square matrix. It's a 3 by 3. The augmented matrix is a 3 by 4 though. And so the diagonal is from the upper left to the bottom right. It's 2, 2, -2. So this example went from a system to a matrix. This next example is going to go from a matrix to the augmented, I'm sorry, from the matrix to the system. So it says, write the corresponding system of equations, then use back substitution to find its solution. Here's what's awesome about this augmented matrix. If you look at this diagonal, it's already all ones, and there are zeros in the first two places on the third row. That means that is the form of z already being solved for. I'll show you what I mean. So when you go to write the system and add the x, y's, and z's back in and the equal signs, you have 1x plus 5y plus 1/2 z equals -24. And then the next row is 0 x's plus 1y plus 3/4 z equals -2. And then the third row, no x's, no y's, just 1 z equals 8. So look, we've already got z solved for. And then the next part of the problem is just use back substitution. So we substitute it back into the middle row. Notice how there was no x there. So now that we know z, we can just plug it in for y. So this is going to be the first part of my work here. Y plus 3/4 8 equals -2. So 3/4 of 8, 3 times 8 is 24, divided by 4, 6. So y plus 6 equals -2. Subtract 6 to both sides, y equals -8. So now I have z, now I have y. The next step is to plug it back into the first equation so I can get the third variable. I've got x plus 5 times y. Now I know y is -8 plus 1/2 z, which is +8 equals -24. Math ensues. So I've got x minus 40 plus 4 equals -24. X minus 36 equals -24. Add 36 and we have x equals 12. So x is 12, y is -8, Z is 8. And we also can write this as an ordered triple, like that. All right, so what we did on this page was practice going between systems form and augmented matrix form. And then we showed how once you can get something in this form down here where there's only one variable left in the third row, that means you can solve for that variable and do back substitution. The issue then becomes, how do I take any matrix and get it to look like this, where the bottom row only has one variable left? And that's something we're going to do more of in the next few lessons. But what we're about to do is take that knowledge we have about elimination in a system and how we can do elimination in a matrix to make any matrix have the bottom row look like that, 0, 0, and then a number. Because once that happens, we already can just solve for that Z variable, okay? We won't be doing that full-on process today, but we're about to just review how you would start thinking about that process. And so we need to talk about row operations. These are called elementary row operations. Elementary just meaning, basic, very Sherlock Holmes. It's elementary, just basic. The first thing is you can interchange any rows that you might want to do up and down. And let's go back all the way to that very first example I gave you. What we're about to talk about is this thing right here, where I was saying that if you wanted to eliminate these x's right here, you could multiply by -2. That's what we're about to, and I said over here, you could do that. You could multiply the row by -2 and add to the row above. If you added them and replaced, if you added here and then got your answer and replaced to that second row, you'd get a 0 right here. All right, so that's our goal, is how do we get zeros in different places of the matrix so that we can start solving. Okay, so, and we use row operations. Like if I say -2 times row 2, that's an operation. It's multiplication. Operations add, subtract, multiply, divide, right? And we're just going to be doing that on the matrix forms. And it doesn't, you can just flip rows around. So if you already had a 0 somewhere, you could just interchange it with another row if you needed the 0 somewhere else. Number 2, you can multiply the entries of a row by any non-zero constant. 3, any 2 rows can be added together to replace one of those 2 rows. So you add 2 rows, you eliminate something, and then once you get that answer, you use it to replace one of the rows. So let's practice a few replacements. So not solving or trying to get 0 necessarily, just practicing what it looks like when you perform an operation and replace a row with that new information. Okay? So for this example, the arrow means you're replacing. So we're going to do 1/3 of row 1 and then replace row 1 with that new information. And we're not doing anything in this example for row 2. So 1/3 of everything in row 1. So 1/3 of everything. So you're basically distributing that through. So 1/3 of 3 is 1. 1/3 of 2, 2/3. And 1/3 of 5 is 5/3. And that new math replaces row 1. And row 2 in this example is not being touched at all. So it just stays the same. Okay, let's practice another one. So we just did one thing here. What we're going to do now is 2 things. We're going to do this first thing here. And then when we go to do the second thing, it's going to be performed on the new matrix we got after step 1. All right, so let's do step 1. 1/4 of everything in row 2 replaces row 2. So row 1 is going to stay the same. And 1/4 of everything in row 2 gives me 1, -2, and 3. So now when we go do the second thing, it's going to be on this new matrix right here, not the original matrix. Okay? And so this double-headed arrow right here just means switch. We're just switching row 1 and row 2. Okay, and that's it for that one. And then we have one last example. So perform the indicator row operations and write the new matrix. So this one's a little bit more involved. We're going to do the first thing first. Okay, so I'm going to do -3 times everything in row 1, add it to 2 times everything in row 2, and that's going to be my new row 2. So even though I'm doing math on row 1, I'm not going to be updating it with anything. I'm using it to do math, but the only row that's going to be changed when I'm done with that math is row 2. So let's look. So -3 times everything in row 1, that gives me -6, -3, +3, and +9. And then 2 times everything in row 2. So that's 6, 2, 2, 0. And now we just add those up and down. 0, -1, 5, 9. And that's my new row 2. So let's look at what that looks like. So if I'm only changing row 2, row 1 is going to stay original, not with the -3, but the original row. So the original row 1 was 2, 1, -1, -3. The new row 2 is right here. 0, -1, 5, and 9. And row 3 did not change. So 4, 3, 2, 3. All right, so this is my updated matrix. So now when I go to do step 2, I'm using this one, not the original one. So using that one, I'm now going to do step 2 here. So -2 times everything in row 1 plus row 3 is going to give me a new row 3. So even though I'm multiplying everything in row 1 by -2, my final answer is not going to change. It's not going to update row 1. I'm only updating row 3. So -2 times everything in row 1 gives me -4, -2, +2, +6. And then row 3 is the same, 4, 3, 2, 3. And I add those up and down. That gives me 0, 1, 4, and 9. So let me use that to update my matrix. So this time I'm only changing row 3. So row 1 is going to stay 2, 1, -1, -3. Row 2 is 0, -1, 5, 9. And then row 3 is 0, 1, 4, 9. And now we're not actually solving this system today, but if you notice, I have these zeros here, right? X got eliminated there. That's one step towards being able to solve for Z and do back substitution. All right. So now we are done.